Thank you everyone for attending and welcome our 20 students in our carbon hack that are tuning in. So this is our last webinar for our grounded growing from CO2 series, and we're looking at biological ways to convert CO2 into some useful products. So we've got three panelists today to help talk a little bit more about this area. So we've got Dr. Jitendra Joshi. Dr. Jitendra Joshi used to be one of the leads for a technology team at NASA. He now works with Woodside, helping them to find ways to effectively use carbon dioxide as well as improve their hydrogen generation. And then we've got two Monash students with us today. So we've got Garv and Rosalie. Both Garv and Rosalie are engineering students at Monash, and over the summer they worked on some research projects with Woodside looking at how to use carbon dioxide. So if we'll, just as a notice for everyone tuning in, we'll have 10-minute talk or discussion points by each of our panelists, followed by 5 minutes of questions. That'll give us about 45 minutes, and then we'll circle back towards the end for 10 minutes of questions that will be for everyone. So Rosalie, whenever you're ready.
Okay, right. I'll just share my screen. So good morning, my name is Rosalie Fang. I am a final year student studying a double degree of chemical engineering and pharmaceutical science at Monash University. I have recently participated in a decarbonization project with Woodside Monash Energy Partnership, assessing the potential for biochemical conversion of CO2. I'll briefly talk about the biochemicals and CO2 utilization project that both Garv and I have worked on and share some of the motivations and experience in decarbonization. In simple words, our ultimate goal is to take waste CO2 and turn into valuable products using biology. Our project aimed to develop a techno-economic model to evaluate the viability of large-scale biochemical CO2 conversions, to create high-value products using microorganisms called cyanobacteria. Cyanobacteria naturally or can be engineered to produce a wide variety of molecules. It offers several advantages as a promising microorganism platform in bio-industrial processes, including simple inputs requirements, high tolerance to salinity and temperature, rapid growth, and great photosynthetic and genetic and engineering capabilities. In the presence of light, CO2, water, and minimal required nutrients, cyanobacteria can produce a wide range of products from pharmaceuticals through specialty chemicals to personal care. The illustration on the screen shows the various products that cyanobacteria can form in different pathways, and the formation of multiple products may be the key to enhance the overall viability of such pathway. Cyanobacteria can produce whole cell derived powder products such as the superfood spirulina and other biomolecules within the cells, for example, antioxidants and astaxanthin, skincare ingredients, squalene, and biofuels. Apart from its intracellular pathways, cyanobacteria can also secrete liquid products that accumulate in extracellular mediums or release volatile gas products that can be captured directly by fragrances. The complexity of product extraction and purification processes are highly subjective to the products of interest and their end applications. In this project, we also performed a techno-economic assessment using our build models on a conceptual industrial scale astaxanthin production. Astaxanthin was selected as the target high-value product for our conceptual study because of its therapeutic benefits, growing demand, and high economic value, which reported to be up to $7,000 per kilogram in nutraceutical grades. Our project outcomes highlights that the biological pathway to CO2 use by cyanobacteria is economically viable, and the use of cyanobacteria clearly offers greater economic advantages producing astaxanthin, at least about 70% cheaper than the current astaxanthin production pathway. Awareness and concerns about climate change have risen significantly across the world in the last decade. Research has been conducted to deepen the understanding of how climate change impacts on ecosystems, resources, and human societies. Identified and significant impacts have motivated and urged community, from individuals to industrial sectors, to take adequate actions in response to climate change. Carbon emissions, particularly carbon dioxide, are known to be the main driver to climate change and global warming. Transition to a lower carbon future is highly desirable and challenging. Among the ongoing research for potential climate change mitigation strategies and pathways, CO2 captures and utilization as an alternative and cheaper carbon source for chemical productions has gained great attention. As a young engineering professional, I would like to be involved in this field to contribute my strengths in finding solutions to achieve our society goals of low carbon economy. Valorizations of CO2 emissions could potentially serve for two purposes: of reducing the net cost or increasing the profits of reducing carbon emissions, as well as providing feedstocks for more sustainable practices. Among the major categories of physical, chemical, and biological utilization of CO2, biological pathway offers unique and attractive carbon utilization potentials and product opportunities. I have worked on several industrial projects through internships and scholarship programs in various fields. In particular, my previous experience at Agriculture Victoria and PhD has allowed me to have a better understanding of CO2 emissions in dairy processing, mining, and land use. My growing interest in carbon management encouraged me to keep looking for more decarbonisation opportunities in the energy and manufacturing industries. I got this amazing opportunity to work on the large-scale biochemicals and CO2 utilization project with Woodside Monash Energy Partnership through Monash Industrial Team Initiative, also known as MITI. MITI offers Monash students unique opportunities that harness multidisciplinary student teams with leading Australian global industrial partners, undertake a specific project for 12 weeks during the summer break. Over the last summer, I was embedded within Woodside Monash Energy Partnership and given plenty of networking opportunities to actively engage with academics and industrial professionals with different expertise. I not only gained some highly valuable learning and project management experience through this summer programs, but also very lucky to be offered an opportunity to get involved in more decarbonisation projects with the partnership as a research assistant during the semester. Some students might not feel confident enough to apply for internships or summer programs as they're concerned that they don't know the topics well enough or have not got all the required knowledge or skills. In my opinion, one would never have all the knowledge and skills needed for a drop project because the specific requirements change at any time and would always learn more as we go. When I first applied for my internships, I have only completed my second year of engineering. I found out that most applicants were postgraduate students or at least final year undergraduate students at the group assessment. I was clearly not as strong as the other applicants in terms of technical knowledge. However, I secured positions with skills that are as important as technical knowledge. I've listed a few examples of what kind of skills that I've used as a student in the recent decarbonisation project. Firstly, good communication is obviously essential for clarifying the expectation of stakeholders, knowledge exchange among team members, and much more. With the impact of COVID, we also needed to learn and improve the way to effectively communicate online. Collaborations and teamwork are also the key skills to expand our knowledge from peer learning and achieve more significant outcomes than individuals. We all know that carbon emissions management and utilization is a challenging problem. Critical thinking and problem-solving skills that were developed through our studies allowed us to approach the problems in a systematic and logical way. Organizational skills such as time management and defining daily, weekly, and monthly goals are critical in project management. Set realistic goals and work towards them step by step. Ensure that you will deliver a high quality piece of work on time. Do not underestimate your potential contributions to solving this global challenge. Before participating in the biochemical CO2 utilization project, I couldn't see myself making a direct impact in this field. And through this opportunity, I am very proud that I contributed my strength in developing a techno-economic model demonstrating the great potentials and feasibility of large-scale biochemical CO2 utilization using cyanobacteria, which is not available in the current literature. When we reach out to various academics, industrial professionals, suppliers, and companies for advice, I thought that we were making an impact spreading the concept of biological utilization of waste CO2 into valuable products, just from their responses that we received. Biological pathways to CO2 use is a rapidly growing and relatively new and innovative area. Lots of studies and research in the early stages in the forms of conceptual studies, computational simulations, and lab-scale operations. At the current moment, as I'm sharing my stories with you and viewpoints in this webinar, I think I'm making a positive impact here too. If you enjoy taking initiatives and interested in CO2 utilization, join us and take on the available opportunities to make an impact yourself on this global challenge that is directly relevant to you and our community. You might like to work on engineering novel cyanobacteria strains in a biological lab, optimizing process parameters for future scale-up, polishing up a business proposal, or programming models for certain biological pathways. To sum up, biological pathway to utilize CO2 offers unique and great potentials. Scalability and commercializations are critical factors for success. Talented students are accelerators to make more significant impacts. Thank you for listening.
Thanks for your presentation, Rosalie. It was very insightful into a potential use for cyanobacteria, as well as how you actually got involved with this project. So for all our attendees, if you have any questions, please feel free to put them into the Q&A function at the bottom of your screen. Or if for anyone watching through the Carbon Hack, if you have a question, please feel free to ask Linus and he will field it through. I'll start off with the question. So I guess kind of biochemical methods for CO2 conversion, people can think that is very, I guess, lab heavy, and you need a fair bit of experience and kind of expertise to be able to work in this area. Because you're a student, and I guess this area would be pretty much new for you, did you get the opportunity to learn a lot about how to actually do this kind of work? Or did you have to rely on your previous experiences, I guess, from what you kind of learned from your undergraduate studies?
So I guess my situation is perfectly aligned with this project in particular, as I have backgrounds in both pharmaceutical science and chemical engineering. So I did have some experience in the labs. However, it wasn't directly related to synthetic biology, which is like engineering a particular strain of cyanobacteria. So I guess lab knowledge or requirements will be beneficial, but not critical in terms of like whether it will stop you from getting such opportunities. Because I guess throughout the project, we've learned a lot more about cyanobacteria. And I guess before that, no one on the team has ever really looked into cyanobacteria as a particular microorganism. I guess microalgae or other algae might be more well-known by the public. And there is a lot of novel strains that are coming up and they might have just only been developed or discovered in the last 5 or even 2 years or so. So I guess, as I mentioned, apart from your technical knowledge, your soft skills and your skills in terms of learning the new knowledge, peer learning, effective communications, to me were more essentials and critical in terms of take up new knowledge and expand the expertise.
Thank you. I think that's good for some of the students to hear that because this is such a new and kind of emerging field of ways to utilize CO2, a lot of people are learning on the fly as well. You don't necessarily need a lot of that technical base knowledge that people think you may need. You can kind of try and take on these projects with a somewhat blank slate and kind of still achieve some benefits. Excellent. So how did you, I guess you got to work with the cyanobacteria. How did you find working with the cyanobacteria in terms of actually processing the CO2?
So our project was more on focusing on the developing the techno-economic models rather than working hand on hand with the cyanobacteria. But I guess the cyanobacteria has its own advantage and disadvantage in just processing or utilizing the CO2. So because of its purity of CO2 contaminations and all in the waste streams, cyanobacteria appears to be more acceptable for such conditions, so they can take up large amount and also not as pure as the CO2 grades. So that's a really big advantage of using cyanobacteria. I guess It also offers a huge advantage in terms of its short doubling time. So in comparison to conventional micro LEDs, can produce, we can doubles in as short as 2 hours in times. So that basically offers a much bigger magnitudes and impact in terms of how applications can be applied and what kind of impact it can put out in an industrial scale.
Okay, awesome, thank you. That's a good point to make, that cyanobacteria can actually handle lower concentrations of CO2. So it'd be quite helpful if you're trying to remove CO2 from the air rather than from a waste stream from industry. Thanks for that. If anyone else has any questions for Rosalie, feel free to put it in the Q&A and we'll circle back to her at the end. We'll move on to Garv next. Garv, if you would like to present.
Sure, thank you. So a very good morning to everyone and a warm welcome. Thank you for being part of the webinar today. I will begin by introducing myself. My name is Garv Bhardwaj, and I'm a final year chemical engineering student at Monash. And I'm an international student, and I came to Melbourne in 2018. I've been part of many volunteering groups throughout my course and being part of an active community, which has allowed me to network with industry and academic professionals while making friends from all sorts of degrees. So these experiences have motivated me to delve into the field of CO2 utilization. While doing chemical engineering, I came across aspects of being responsible as an engineer for the benefit of the community by ensuring safe and sustainable environment. So using creative solutions as well as engineering standards, I wanted to tackle global issues. And while this relies on the knowledge I gained, I lacked the experience for it. Therefore, I was highly interested in undertaking a role where my contributions addressed an important issue and I could provide a viable solution as well. So this brings us to the global issue of climate change. And as defined by the United Nations, climate change are the changes occurring in the environment because of human activity that affects the ecosystem by creating climate variations over a long period of time. So the primary factor, obviously, you guessed it, is the increasing concentration in atmosphere of CO2. So to create a low carbon future, there were several techniques that have been adapted, mainly including efficient resource utilization, relying on renewable energy, and also removing CO2. And the older CO2 techniques relied more on capturing and storing. However, this was not very economically feasible. We need to tackle climate change in a more sustainable way by adhering to more people, profit, and environment aspects, which would also work efficiently in the long term. Therefore, this leads down to formation of carbon capture as well as utilization, also known as CCU, where carbon is captured or CO2 is captured and converted into valuable products. Now that we've had an overview of CCU, let me briefly discuss the project Rosalie and I undertook over last summer as part of the Monash Industry Team Initiative, or MIDI project, under the Woodside Monash Energy Partnership. So quickly briefing again from Rosalie, it was a part of the partnership's decarbonization theme, and the project revolved around biochemical conversion of CO2. And it was more about understanding the biochemical pathway of CO2 conversion from a waste CO2 stream within any industrial plant. We were then tasked to prepare technological and an economic report in form of a techno-economic model, which involved designing a process for extracting valuable products from the biomass that we grew during cultivation, as you saw from Rosalie's presentation. So one of the highlighting aspects that we found while studying CO2 valorization was the sheer magnitude of CO2 that is actually emitted in Australia. And this was just in Australia. And imagining it on a global scale gave us a really challenging image of tackling climate change. The project was successful, and we identified key factors that determines the feasibility of commissioning a large-scale biochemical conversion plant. So throughout the project, I was extremely fascinated with the technology and the current demand to grow photosynthetic organisms, such as microalgae as well as cyanobacteria. and also the sustainable benefits of this process. So I requested the partnership to continue researching in this field and decided to undertake biochemical conversion as part of my final year research project. So in order to grow biomass efficiently, controlled environments can be simulated that are actually in form of photobioreactors. And in very simple words, these are bioreactors equipped with light. So my research mainly delves into parameterizing how cells, microalgae cells, and bacteria cells in these photobioreactors experience light as they move around. And I simulate this on these reactors on a software, and then I can validate them with the data from experiments that I conduct on the actual reactors. So as a result, I can assess the performance of different photobioreactors. And as you can see, an image on the left, which is of a stirred PBR, photobioreactor, and it's very similar to a mixing tank, except there is presence of light. So now that I've discussed my projects, I would like to tell you a little bit about the experience I gained from working in this field. So as a chemical engineering student, single degree chemical engineering student, there were times that we were taught briefly about bioprocessing and sustainability processing, but most of the times these concepts remained unknown to me. So as you can see on the about the learning curve on the right, when I started the Mighty project, I was more in the I was quite interested phase. And as soon as I got into a few weeks into the project, I soon realized that it was more complex than I had initially imagined. And learning your concepts with the help of my supervisors as well as teammates, it only got more challenging before it started to become more clearer and it started to make sense. In terms of finding reliable technological data, modeling equations, and even equipment costs was a major challenge due to the lack of commercialization in this field. We contacted various suppliers, researchers, and fabricators, as Rosalie indicated, to gain a basic idea of the current status of the biochemical industry. However, over time, we acquired relevant knowledge and experience of tackling these issues, and also were able to create a network of people with similar interests. Overall, the knowledge I gained from the Mighty project was much more than I had initially imagined. Towards the end of the project, I was only more interested in delving deeper as I felt responsible for the planet and how I could contribute as an individual. I'm sure many of you have felt that from time to time, and it is imperative that your actions will make an impact, whether you have started years ago, you start today, or you start years down the line. The network of people I made through the Mighty project and also continuing down into my research project has been very beneficial. Some of these individuals, like Jitendra here, have made a very significant impact on society. And we can only learn, move, and take the torch forward. Climate change is a phenomena that connects everyone because everyone is affected by it. Therefore, I always advocate and spread awareness about climate change and how everyone can contribute towards fixing it, irrespective of the fields. But just being a responsible engineer, you can apply sustainable principles and in your everyday working, and always support the methods that positively contribute to society. Finally, I just want to show you an image. The image on the right is of Christian Haflidason, who's the CEO of Algae Innovation. He's overlooking a photobioreactor, and it is one of their microalgae production facilities. This inspires me because it takes me back to the quote that my supervisors always point out, is that the 21st century is the age of biology, and it has transcended from mathematics, physics, and chemistry. And the advances in biological application are numerous. The major ones that I find relevant to chemical engineering or even for CO2 conversion lies in producing biomass efficiently and also being able to engineer strains of microalgae or cyanobacteria, which can produce high density biomass or products that are valuable. So in conclusion, the biochemical conversion is a highly sustainable method of carbon conversion with a very strong potential into the future. Thank you.
Cool. Thanks for your presentation, Garv. It was very interesting, and it was great to hear more about the project you worked on and a bit more about the biological methods. So just to reiterate, if you have any questions, feel free to put it in the Q&A function or ask Linus, and he you can bring them up to the panel. So just to start off, so would you be able to explain a bit more, if you can, about what you guys kind of found about with your techno-economic assessment about cyanobacteria? I guess there is a very traditional view that using things like algae or even cyanobacteria can be quite expensive because there is a lot of work. But you guys managed to find it to be a bit more feasible. Could you kind of elaborate more on how you guys got to that?
Yep. So it comes down to the actual strains that we are using to produce the biomass. So depending on the type of microalgae or the type of cyanobacteria that you use, you can vary the conditions that they can survive in. You can vary the doubling times. You can also vary the type of products that they will make. They can make extremely valuable products. They can make terpenes. They can make hydrogen, which are very valuable in addition to them creating biomass. So you are actually creating multiple products just from one waste stream of CO2.
Okay, awesome. So I guess to elaborate on that a bit further, what kind of parameters did you guys find to be critical for consideration to make sure things are actually feasible?
So I guess the major parameters that come down is the light that we use, because light is a very important aspect for photosynthesis, and these are photosynthetic organisms. So the delivery and optimization of light is very important, and that comes down to the photobioreactor, where the cultivation of the photosynthetic organism occurs. Some other could be the nutrient that you provide for the biomass to grow, because cyanobacteria can have a tendency to bloom if there is an excess of nutrient. It is very important to control those nutrients. Finally, CO2 concentration, because ideally we are trying to utilize a waste stream and we're trying to reduce the amount of CO2 that goes into the atmosphere. We want to capture as much CO2 as we can. So that becomes a very important parameter as well.
Okay, awesome. And I guess you highlighted a kind of very important point at the end of your presentation, how we're kind of progressing to a more biological age rather than a very, I guess, very physical kind of technology basis where we're using biology to kind of really solve our problems. And I think that highlights quite an important point that as we're developing ways to utilize CO2, it's not just an engineering problem anymore. There are opportunities for microbiologists, biologists, biomedical scientists as well to kind of integrate what they're learning as well into this field to be able to solve one of our big problems rather than using what they know just kind of for other things. Just to be conscious of time, we might move on now. Thank you, Garv, for your presentation. If anyone thinks of any other questions they would like to ask us, please feel free to put it in the Q&A and we'll circle back to it at the end. So we'll now move on to Jitendra. So Jitendra is a highly renowned expert in this kind of area, and he's been able to help Woodside kind of progress their development of this area quite substantially. We're going to take a little bit of a different format for Jitendra here today. And if anyone has any questions they would like to ask Jitendra, please feel free and we can kind of provide some insight and perspective. Jitendra, is there anything you would like?
Yeah, I would like to say a couple of things. Basically, Garv and Rosalie and the team, they showed you a journey of, and I like one of the graphs that Garv had. You know, you are enthusiastic about something. You say, "Oh, I'm going to change the world tomorrow." It's just all me between changing the world and me being able to do is tonight's sleep. That's it, right? And a meal. But no, it's not that easy. And the realization that of learnings that you went through your journey is extremely important. One thing I would like to add here is the two presenters gave you a very nice idea of techno-economics and biology and engineering design and reaction engineering. I would say 21st century is a century of systems engineering. And what do I mean by that? Systems engineering is not a discipline in its own. Systems engineering is a way of thinking. What I would like you folks to be challenged with one thought is there is no one solution to a problem set. many a times we will create a solution and create more problems. So start thinking on the ramifications of CO2 as is not a one solution set. We can't just grow algae and astaxanthin and terpenes. The prices will come down if I convert all the CO2 in the air into these products. It's a multi-pronged approach. So when you think of solution sets, think of integrating multiple ideas into a common theme. As an example, Garv said lighting is one of the major issues. In my life, I worked on high pressure sodium vapor lamps, not thinking of the system's impact on it, right? But they are very high energy, they radiate a lot of heat. So you've got to think of the thermal subsystem. That's when LEDs came into NASA. And NASA was the pioneer in developing LED technology for plant growth. So going back to this, now start thinking from an Earth perspective. There is going to be energy involved in trying to make the lighting system. I'm just picking on this example, right? Now, how do we, don't forget where the energy is coming from. It, like food doesn't come from the supermarket, right? It grows in the fields. Just because you plug it in, start thinking backwards. Where did that come from? Did fossil fuels go into burning and making that electricity? How can I change that? What is the role of renewables? So again, what I'm trying to tell you is think from a systems perspective. CO2 is not a one solution set. It's not a one problem. It's a multifaceted thing. And my advice to you guys is you're a multi-disciplinary team. Interact with each other. Be nosy about each other's work. And I say that in a nice way. And learn, adapt. If you think you're going to be a specialist and survive in the 21st century, I got some news for you. You're going to be a dinosaur by the time you finish your degree. Okay? So try to fail early, try to fail often. This is your time to do it. Okay?
Thanks for those points, Jitendra. I think that's very insightful and good advice for people to take on board. We do have, just to lead on, with your position in Woodside and being able to help progress their CO2 conversion and utilization, I think you may be able to provide some insight into some questions that some people have, especially in terms of like biological risks. So I guess Garv and Rosalie talked about using cyanobacteria, which is quite helpful because it already has natural mechanisms to actually convert CO2. But there are multiple other biological ways to actually utilize CO2 as well, like with different enzymes or engineering other microorganisms to kind of process the gas. But where do you see some of the challenges in mimicking nature to actually utilize and convert CO2, and why has it actually been difficult to achieve on a large scale so far?
So one of the things, so let me go to your last point first and then work backwards, okay? And I'll try to be as succinct as possible. One of the biggest challenges in utilizing CO2, there is a lot of CO2 on this planet. Since I was born, it has increased 30%. So you can figure out my date of birth, right? However, although it is 411 ppm or thereabouts, it's a very hard, CO2 is a very stubborn molecule. It's very hard to capture at such low concentrations and concentrate it. So one of the big challenges has been direct air capture. And I'm not making this up. There are National Academy of Sciences reports that you guys can look at. There's a lot of literature in this area. So one of the big stumbling blocks and why we are not able to use CO2 on an industrial scale is capturing the CO2, the energetics that are involved with it. It takes about $200 to $300 US to concentrate that 400 ppm CO2 into a very concentrated stream of 95 to 100%. Okay, that's one challenge. So one way to address it is go to the point source as much as possible. 15 or 20% of CO2 on this planet is emitted at point sources of industrial manufacturing processes. That's one way to do it. Other way is also do advances in direct air capture and sorption and desorption of CO2. With respect to biochemical pathways and exploitation of this, about 10 years ago, it was a hard thing to do. With the advent of molecular techniques like CRISPR-Cas9, for which Nobel Prize was awarded last year, we have been able to modify organisms, insert very high functioning molecular genes into fast growing organisms, increase the doubling time, as Garv and Rosalie said, by putting that in the molecular chassis. So that is catching up. Listen, there's one reality. We're going to be a population of 10 billion within the next 30 years. The land mass on this planet is not increasing. We have to feed these people. There is CO2 in the air. Nature does it with plants. Nature does it very slowly. We have to speed up that process. And the only way to do that is using molecular techniques along with fast-growing organisms. So, Brian, I think these challenges are being overcome. There are several industries right now doing this on an industrial scale and very well. The advantage of biology is it's resilient. It can recover from failures pretty well. The disadvantage is evolution doesn't like change. So you have to actually make these organisms do what you want, and it's become easier. So there have been challenges. 10 years ago, your question was, I don't know, would be the answer. Today, we say we know what the challenges are and we have the tools to do it.
I think that's a great point, that because as time progressed, other technologies have developed, and especially in the biological space where genetic engineering techniques such as CRISPR have kind of evolved and emerged, it now gives us greater potential to be able to use different technologies to convert CO2. So now biological methods with the genetic engineering potential is now looking a bit more viable and looking more like a successful possibility to be able to utilize our large amounts of CO2 in the air. So I think we have a good question from Russia that will kind of lead on to that kind of point. Jitendra, would you be able to elaborate a bit more on the current best biological pathway for CO2 conversion and what kind of the efficiency is? So for example, potentially in these kind of metrics, how much CO2 can be converted in an hour, or how much area of cultivation is needed? And just to kind of lead on from that question,
I'm going to give you an example. When is the last time somebody had a burger? And the answer is last week, right? So think systems. We eat a burger, we're done with it, right? We order medium rare, we are done with it. What I would like to challenge you is, where did that burger come from? What went into it? A quarter-pound burger actually consumes about 2,000 liters of water. I'm asking you to think systems. The burger came from a piece of meat from the cow. The cow has an efficiency of 20 to 25% in eating grass to converting its biomass. Not all the biomass of the cow is eaten into the burger. There is a big acreage of field that the cow has to graze on. All the life cycle costs you about, to create 40,000 tons of protein, it requires about 100 square miles. I'm sorry, I'm still doing miles and kilometer conversion here in my head. But significant amount of area. To make that same amount of protein using biological pathways with bacteria, it requires only 0.04 square kilometers of land area. You recycle 80% of the water. That's for food. We traditionally make ethanol via fermentation processes using simple sugars, right? Right now, sugar is cheap. I'm talking of glucose. But sugar is also food for humans. What if I convert that CO2 into some intermediate blocks and deploy molecular pathways of fast-growing organisms to make that alcohol? That is happening. There are chemicals such as isopropanol alcohol, butanediol. All these are being made with starting as CO2 as the starting product. Sometimes they make an intermediate product like CO and syngas and then feed it to the organism. So the footprint is really low. The energetics are favorable. From a systems perspective, biology is 10 to 50 times less energy intensive and leaves a 10 to 50 times less of an ecological footprint. What it gives is it requires more time. Most chemical engineering processes are flash processes, they occur in seconds. This will require hours or days, but you don't have the high temperature, high pressure, and therefore the energetics are favorable for biology. If you are able to target one molecule and produce that successfully repeatedly.
Yeah, thanks, Jitendra. I think that's a bit enlightening. I think Rosalie and Garv kind of mentioned this before, that in the techno-economic assessment for using cyanobacteria, they were looking at producing some high-value products. How can we kind of, I guess this is open to anyone, how can we kind of determine some high-value products to produce through biological methods? Because I guess that kind of really helps to improve the viability of these processes.
Rosalie, you want to go first?
Sure. So it really depends. So there's thousands of different streams of microorganisms, even within the same categories. So it really depends on, I guess, what kind of market is predicted, what demands are in the current market, and ultimately, and you might take inspirations from existing biological production pathways for other mechanisms, organisms to implement similar conditions or engineer a similar biological metabolisms pathways to existing ones and modifying that can produce the products in demand. So I guess for over the last few decades, people have been paying more attention into, I say, for example, nutraceuticals product, a lot more into maybe for women's, a lot more into cosmetics, skincare, and things like that. So those ones are potentially in very high product markets. And I guess the transitions from public's point of view of purchasing the petroleum-derived products into more organic and sustainable derived products is rapidly growing, and so that sense that customers and customers are more willing to pay for a premium price for such premium produced products. So it comes down to a lot of market research, also try to align the markets with products that can be produced by a certain strain of microorganisms.
Awesome. Thanks, Rosalie. Do you have something you'd like to add, Garv?
Yeah. Just want to add in that high-value products can also be in terms of products that are formed through chemical synthesis or through chemical pathways might be expensive because of the way that they're produced, and they might actually be cheaper if produced through organisms. And another thing would be if you look at, let's say, biofuels from the past few decades. It has been one of the most popular ways to produce fuels, and it has also rising into popularity. However, if you do look deeper into it now, strains are actually being able to produce hydrogen, and now that would probably go to the next level of energy transition, where you're transiting from liquid fuels onto hydrogen fuel as a fuel. And so it also depends on where the market is driving towards. So that's what defines the market value of that product.
Awesome, thanks, Garv. I think Rosalie and Garv make some good points, that biological methods have kind of opened up the avenue of different products that we can actually make from CO2. I guess that is kind of a disadvantage of chemical pathways for utilizing CO2. Traditionally, a lot of those only make other chemicals that have more industrial applications or low end use rather than having high value. Whereas biological methods, we can actually make different products that can go into cosmetics because they're relatively safe. So that just kind of opens up the creativity for scientists as well as researchers about the different products we can actually make from CO2. So I think a good example of that kind of emerging industry is in Australia, we have a huge algae farm that looks at making beta carotene, which is a nutraceutical, but it uses algae, which is able to convert the CO2 into a beneficial product. So there is a huge scope for especially, I guess, young scientists to be kind of creative about the different chemicals they can produce. We're no longer limited to trying to replace petrochemicals and produce alternative fuels, but we can make different additives, different food supplements, or different cosmetic reagents that will serve other purposes as well. So if anyone has a question for any of our panelists, please feel free to put in the Q&A. I guess another question that we can kind of field out to our panelists is, where do you guys see the future of, I guess, biological conversion heading towards? Yeah, yes. Jitendra, maybe do you potentially have some perspective into where the future of biological conversions can kind of lead to and where it can kind of develop into?
So I think that the possibilities are endless, and we will be compelled to use biological pathways as opposed to today it's a choice. Today it's there are pioneers who are trying to do it, but just like in 1913, when Haber invented the ammonia process, making ammonia with hydrogen and nitrogen, did not imagine that that would be the only way that fertilizers would be made. And I think we are at that stage in terms of synthetic biology, in terms of making, in fact, the Defense Advanced Research Projects Agency, DARPA in the US, actually started a program called Living Foundries about 7 or 8 years ago, where they challenged researchers to make 50 molecules which are really high, 1,000 molecules which are high commodity molecules. And I think they got to about 100 molecules that are really hard to make chemically. They're very expensive to make chemically. And they're essential molecules, as Rosalie said. She gave some examples. And so the possibilities are endless. It is not going to be a matter of choice. It's going to be how fast we get there. And that's why many oil and natural gas companies around the world are actually looking at biological ways to not just sequester, but to transform CO2 into useful products. And CO2 is the primer molecule, which is available ubiquitously.
Yeah, thanks for that, Jitendra. Garv or Rosalie, do you have anything you'd like to add?
Yes, so I guess it's a biological pathway of utilizing CO2 is relatively fields and emerging field of study. However, you can already see a really great progress along the lines in the last 10 or 20 years. For example, for the microalgae now that built plenty of successful microalgae farms or bioprocess plants that producing commercial products at a very large magnitudes. And there's also, you can also start to see the current transitions of using open ponds and to produce such microorganisms to more sustainable ways of producing them and cultivating them called bioreactors, which would take up a link back to the previous question, that it would take up a lot less land requirements, and as there can be vertical configurations, and I guess the optimization of how you structure and the bioprocessing plant will potentially speed up the biological pathways of utilizing CO2.
Thanks, Rosalie. Do you have something you'd like to add, Garv?
Yep. So as I said from the presentation itself, we are actually closer to understanding more about these organisms and how they work, because they work on multiple, they require multiple things, and it gets complex at one point. But I think at this point, we're starting to de-link everything and understand all the important factors that are going to affect the growth. And we can simulate an environment where we can control it, similar to like a chemical process. So I feel like this is going to be the next step towards an improved sustainability in the future.
Okay, thanks, Garv. So if there are no lingering questions, I think we can end the webinar there. I'd like to thank our panelists for taking the time out of their busy schedules to come and present for us today. And I think you guys have highlighted a very important point about biological pathways. You don't need to be a chemical engineer to be able to come up with an effective way to utilize CO2 anymore. Because of how science and technology has developed over the past couple of years, the opportunities are available for a lot more people and a lot more researchers to actually come up with an effective way. So don't be disheartened if you don't know a lot about process engineering or chemical engineering. Even biologists, microbiologists, and potentially other forms of engineering can now really develop and implement a strategy to utilize CO2 effectively. So I hope that was an enlightening presentation for everyone. And thank you all for attending. This recording will be up on our website and YouTube channel soon, so be sure to check out if you missed anything. But yes, thank you all for attending, and thank you to our panelists for taking the time.
Hey, Brian, can I just say one last thing, please?
Yeah, sure.
I apologize. I know you're trying to wrap up.
No,
I want to leave you guys with a challenge. My parents' generation started messing it up a little bit with the planet. For being a little bit unparliamentarian, I would dare to say my generation actually screwed it up really bad. It's up to you. Think of the responsibility you shoulder in terms of trying to make an effective change. And that change begins with you. As Brian said, you don't have to be a specialist, and I would urge you not to be a specialist. Think from a systems perspective. If you don't remember anything from this talk, I would urge you to remember one word: case, cause and subsequent effects. Anything you try to do, your research, and we need people from all streams. It is not a scientific problem. It's a political, it's a social, it's an economic. Technology will it's the least important thing. So try to think from a systems perspective and think whatever you do, whatever actions you do in trying to make a change, think it from all the secondary actions that it will result in. Okay? You are the agents of change, and I made some changes in my life from what my job was in order to be a small catalyst in people like you. So thank you for the opportunity, and dare to change, dare to fail. Only then you will learn.
Thanks, Jitendra. I think those are great words to leave this webinar on, and I think it will help to inspire some of our participants in our carbon hack to come up with some great ideas and some potentially great solutions.